We're going to talk about nuclear kinetics. Nuclear always follows first order kinetics. That means that, for example, we could use the integrated rate law, where the n sub 0 is the original number of nuclides at time t, and n is the number of nuclides remaining at time t. Again, it follows first order kinetics always. So the half-life would be T1/2 equals 0.693 divided by K, where K is the radioactive decay constant. So let's do a problem. We've got a half-life of 67.0 hours, and the question is asking how much of a 1 milligram sample of it remains after 335 hours. What I like to do is first check and see how many half-lives that is. So I take the 335 hours, divide by 67 hours, I get 5 half-lives. That means that I can take my 1 milligram, multiply by 1/2, times 1/2, times 1/2, times 1/2, times 1/2. That will be 5 half-lives. And then I get my answer. Let's look at another problem. We have a 1 milligram sample. We have an activity of 1.7 times 10 to the minus 5 curies. The question is asking for the decay constant. So I would give you that 1 curie is 3.7 times 10 to the 10 nuclei per second. You need to recognize that nuclei per second is a rate. We know this is first order, so the rate would be rate equals rate constant times our nuclei. We want to find the rate given the number of curies. So 1.7 times 10 to the minus 5 curies times 3.7 times 10 to the 10 curies per second. Our curies would cancel. We would get 6.3 times 10 to the 5 nuclei per second. Now we have the rate. We need to find the number of nuclei. 1.0 times 10 to the minus 3 grams divided by the atomic mass, 99 grams. So notice our grams cancel. 1 mole, and in 1 mole we have 6.02 times 10 to the 23rd nuclei. So our moles cancel. And we get 6.1 times 10 to the 18 nuclei. Now we can put that into our rate law, and we can solve for the rate constant. So here's our rate. Here's our amount of nuclei. We have one equation, one unknown. So we get our answer, which is our K. Okay, let's look at radioactive dating. Specifically, we're going to look at carbon-14 dating. So carbon-14 is produced in space. Nitrogen 14 combines with a neutron like this, gives us our carbon 14 plus a hydrogen. Then the carbon 14 reacts with molecular oxygen to get carbon dioxide. This carbon dioxide contains the carbon 14. The carbon dioxide is used in photosynthesis to make glucose. The carbon 14 to carbon 12 ratio is constant while something is alive. So carbon 14 becomes incorporated into plant substances and the animals which eat the plants. As long as the plant or animal is alive, its ratio of carbon 14 to carbon 12 atoms is constant. At death, an organism will slowly lose carbon 14 by radioactive decay. Consequently, carbon 14 dating can be used for a variety of objects. For example, wood, paper, cloth made from plants. You're going to want to write this down somewhere. The half-life of carbon 14 is always 5,730 years. So let's do a problem. The problem is giving us charcoal that's from a tree, and it gives a carbon 14 of 7 disintegrations per minute per gram, and present day carbon gives 15.3 disintegrations per minute per gram. We're asked to determine the rate of the volcanic eruption, which is what killed the tree. So remember, nuclear always follows first order kinetics. So you can use the integrated rate law for first order. So here is our rate law. We have natural log of rate sub 0 over rate sub t. So the rate sub 0 is the carbon 14, carbon 12 ratio at the time of death, and the rate t is the carbon 14, carbon 12 ratio now. So we solve for the rate constant using rate constant equals rate constant equals 0.693 divided by the half-life, which is 5,730 years. So our K equals 1.21 times 10 to the minus 4 per year. We substitute this in, and that gives us natural log of 7 over 15.3 equals 1.21 times 10 to the minus 4 per year times t. So now we can solve for t. This is what we get for t. So all we need to do is take the current year and subtract 6,462 to find out when the tree died. We'll do nuclear transformations next time.